Today we're going to talk about end behavior and multiplicity. By the end of this video, you should be able to determine the end behavior of a polynomial just given the equation, and you should be able to determine the nature of the roots of a polynomial. So here we have four equations and their graphs. We're going to take a look at their leading coefficient, their degree, and their end behavior, and trying to come up with a general set of rules. So for the first equation, our leading coefficient is 2. We're going to abbreviate leading coefficient as LC. The degree is 4. Now we talked about end behavior earlier this year. Remember that we always have, as x approaches infinity, f of x approaches blank, and as x approaches negative infinity, f of x approaches blank. So as x approaches infinity, that refers to the right side of the graph. You can clearly see that the graph is going up on the right. As x approaches negative infinity, refers to the left side of the graph, and you can clearly see that the graph is going up on the left side as well. So both of these will approach positive infinity. Let's take a look at the next one. Our leading coefficient is -2. The degree is still 4. And if we look at our end behavior, as x approaches positive infinity, so on the right side of the graph, it's going down, so this will approach negative infinity. And as x approaches negative infinity, f of x approaches, so on the left side of the graph is also going down, so this is also approaching negative infinity. So these two have the same degree, but the sign of the leading coefficient is different. So take a minute to think about how that affected the end behavior of the polynomial. If we look at the next graph, our leading coefficient is -2, and our degree is 3. Our end behavior, as x approaches infinity, so the right side of the equation is going down, so it's approaching negative infinity. And as x approaches negative infinity, so the left side of the graph is going up, so that is approaching positive infinity. Then the last of these four graphs has a leading coefficient of 2 and a degree of 3. If we look at the graph, as x approaches positive infinity, so on the right side of the graph, it's going up, and as x approaches negative infinity, so the left side of the graph is going down. So for the second two graphs, again, the only difference is the sign of the leading coefficient. See if you can figure out how that affected the end behavior. Then take a minute and look at the two graphs that both had positive leading coefficients, but their degrees are different. How did that change the end behavior? We'll look at the two graphs that had a negative leading coefficient, but different degrees. See how that affected their end behavior. So, after looking at those graphs, the leading coefficients, the degrees, and the end behavior, hopefully you can come up with a couple rules. So, if the leading coefficient is positive, that means the graph is going up on the right. If there's a negative leading coefficient, it means the graph is going down on the right. If the degree of the polynomial is odd, that means that the ends are going in different directions. One is approaching positive infinity, the other one is approaching negative infinity. If the degree is even, then the ends are going in the same direction. This is true of both fourth degree polynomials and quadratics, which are second degree polynomials. So, without graphing, let's state the end behavior of these functions. So for this first one, we have an even degree, so we know that the ends will be going in the same direction. We also have a positive leading coefficient, which means that the right side is going up, and since the ends are going in the same direction, both are going up. So as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x approaches positive infinity. The next example has a negative leading coefficient and an odd degree. So this means that it's going down on the right, so we can go ahead and write that out. It's going down on the right, and then since it's an odd degree, the ends are going in opposite directions. So that means the left side is going up. Now, we can also write the end behavior in words. If I have an equation, g of x equals negative x to the 7th plus bx cubed plus c, so it doesn't matter what b and c are, we can fill in the blanks to this written version of the end behavior. So we know that the leading coefficient is negative. That means it's going down on the right. And remember, the right side is the positive infinity side. So it's going down. So f of x approaches negative infinity. Then we have an odd degree, which means that the other side is going in the opposite direction. So as x approaches negative infinity on the left, f of x is approaching positive infinity. Now let's take a look at multiplicity. Multiplicity is when a graph has multiple of the same root. So when a polynomial has more than one, of the same root. So we encountered this a couple times when we did quadratics. You might solve a quadratic and end up with the factors x minus 3 and x minus 3. So you get x equals 3 twice. This is called multiplicity. So we have this example here. We have the equation, we have the graph. We want to figure out what are the real roots of this polynomial. We can look at the graph and see that the polynomial touches the x-axis at -1, 2, and 4. We could also look at the equation. We have a factor of x minus 2, which will give us a root of 2, a factor of x plus 1, which will give us a root of -1, and a factor of x minus 4, which will give us a root of positive 4. So either way, our roots are -1, 2, and 4. So what is the multiplicity of each root? So if we look at the polynomial, if we expanded this, we have x minus 2, x plus 1 squared, which means we have x plus 1 twice, and x minus 4 cubed, so x minus 4 is 3 times. If you solved this, how many times would you get the answer -1? You would get -1 twice, because x plus 1 happens twice. So this one has a multiplicity of 2. How many times would you get the answer 2? Just once. So that has a multiplicity of 1. And how many times would you get the answer x equals 4? You would get that 3 times from each of these 3 roots. So it has a multiplicity of 3. So then let's look at the graph and see how the multiplicity affects the appearance of the graph. So it says, what does the graph look like at each of these roots? So if we look at -1, the graph just touches the x-axis. And if you zoom in, it would almost look like a parabola if you covered up the other part of the graph. So this one just touches the x-axis. Kind of like a parabola. If we look at 2, that just looks like a normal root. It goes right through the x-axis. It doesn't do anything weird. So this goes through the x-axis. And then if we look at 4, it goes through the x-axis, but it kind of squiggles through the x-axis. It almost looks like a cubic function there. So it goes through the x-axis, almost like a cubic. So, if you think about it, when the multiplicity was 2, it looks like a parabola, which is a second-degree equation. When the multiplicity is 1, it just goes through it, almost like a linear function, which is a first-degree polynomial. And when the multiplicity is 3, it goes through the x-axis and looks almost like a cubic, which is a third-degree polynomial. The last question is, what is the degree of the polynomial? Now, we said that you figure out the degree by looking at the highest exponent, but that's only when it's written in standard form. And we don't want to have to multiply out 6 factors to try to write this in standard form. That would be horrible. The easiest way to do this is to just add the multiplicities. You add 2, 1, and 3, and you get 6. And if you think about it, it makes sense. The fundamental theorem of algebra says that the number of roots is the same as the degree. When it's all written out like this, we'll get 6 roots, even though some of them repeat. So we should have a 6th-degree polynomial. Let's take a look at one more. So here we have the graph of this 4th-degree polynomial. We're asked, what are the real roots and their multiplicity? Well, by looking at the graph, it touches the x-axis at 5. And since it just touches the x-axis, and it kind of looks like a quadratic, it's probably has a multiplicity of 2. According to the fundamental theorem of algebra, how many roots will this polynomial have? Well, remember that the number of roots is the same as the degree, which is 4. So we should have 4 roots. But we only have 2 that are accounted for. So, how many non-real or complex roots does this polynomial have? Well, if it should have 4 and we only know of 2, it's got to have 2 non-real roots. Make sure that you review domain, range, end behavior, x and y intercepts, increasing and decreasing intervals, all of those characteristics of functions that we did at the beginning of the year, because we can also look at the graphs of polynomials and determine all of those characteristics. But I'm not going to do an example of that because that should be review for you.